In Lesson 6, we're going to look at compositions of functions. In Lesson 5, we looked at how to do operations with functions. So compositions is kind of like a fifth way of combining two or more functions. However, it's not just adding, subtracting, multiplying, or dividing. Compositions mean you're taking one function and you're inputting it into another function. And then whatever you get out, you can input into another function. So it's just this process of taking a function and inputting it into another function. So the notation looks like this. So we have f of g, this little circle here, you would read it as f of g of x. Really means you're taking function g of x and you're plugging it into the function f. So x is the input that goes into g, and then it goes into f. So if you think of it as a machine, it would look like this. We would have x going into the machine g, or the function g, and then whatever you get out is called g of x, and then you take this g of x as your new input going into the machine f, or function f, and then your output becomes f of g of x. So you can start with x going into function g and then getting out f of x and taking that output and plugging it into g, and you get f of g of x. So it doesn't have to go f of g of x. It can be flipped into g of f of x. That's fine too. But one thing to note is that compositions of functions are not always commutative. So that means you can't, the order does matter. So if we plug into g and then f, that doesn't mean we're going to get the same result as if we plugged into g or f and then g. So just kind of keep that in mind. So let's go ahead and let's look at some examples. So first thing, again, this notation, you would read it as f of g of x. So this open circle, you know, means composition, and it's similar to saying like your set of parentheses. So you can rewrite it as f of g of x. So x is the original input, goes into g, whatever you get out goes into f. So you're taking, or you're inputting g of x into this function f. So looking at this example, the first thing I'm going to do for a here is rewrite it as f of g of 2. So again, that open circle means it's a composition. So first thing we need to do is we need to work in the inside and then outside. So you always start in the inside and then inside out, basically. So I'm going to take an input. This notation here, g of 2, means input 2 into function g. So I'm going to keep the f. And then what I'm going to do is I'm going to evaluate this, g of 2. So that means I'm going to go up and I'm going to take 2 and it's going to go into function g. So it's going to be negative 4. We're inputting a 2. We're just substituting a 2 in for x. And then again, I'm going to continue this notation outside. So this inside part is exactly what we did before. But now we just, whatever we get out, we have to plug it into another function. So you do negative 4 times 2 minus 6 is going to give you negative 14. So now I'm taking negative 14 and I'm taking that and I'm plugging that into f. So the result of g of 2 goes into function f. So function f I get from up here. So 2 times negative 14 plus 1. So I just plug in negative 14 into function f. Evaluate that and you get negative 27. So that's it. So it's basically, you're just doing one function, evaluating one function, your result goes into the other. So for B, this really means g of f of negative 1. So the difference in this one is the order is different. So we have to pay attention to the order because, again, remember, compositions are not commutative. So that means we have to start with f of negative 1. So I'm going to take negative 1, I'm going to plug it into function f. So we're going to just keep this g on the outside. So negative 1 is going to go into function f. So we evaluate that, and we get negative 1. So now I'm finding g of -1 because -1 is the result. It just so happens that it was the same number, but -1 is the result of f of -1. So now you're going to take -1 and plug it into function g. So we have -4 times -1 minus 6, we get -2. So the next one here, we have f of 13. So basically we're taking and we're evaluating 13 into function f, and then whatever we get out, we're going to put it back into function f. So we're using that same function twice. So it's the same idea, it's just using function f twice. So start with the inside, and you're going to plug 13 into function f. So we have 2 times 13 plus 1. So evaluate this. We get 27. Take 27 now and plug it into function f again. So we have 2 times 27 plus 1. Evaluate that, we get 55. The next one here, f of g of x. Notice this time we don't have any numbers. So the first thing we're going to do is still evaluate the inside. So we have f, and the inside is g of x. Take x and input it into function g. So if you replace x in function g with x, it's going to be exactly the same thing. So it's just going to be -4x minus 6. So basically whatever's in parentheses here, you're substituting in. So I should have an x in this expression that I substituted into. And now what you're going to do is you're going to input -4x minus 6, this whole entire thing, into function f. So this whole entire thing is going to go into function f. So the first thing I'm going to do is look at function f, 2x plus 1, and I'm going to rewrite that, but instead of writing x, I'm going to just put my parentheses. And normally we put the number in here, we put the x in here, but in this case I have -4x minus 6 that needs to go into that. So -4x minus 6 is getting inputted into this function rule 2x plus 1. So now it's just simplifying. So once you get this part, you're just simplifying. So you're going to distribute. So we have -8x minus 12 plus 1. So you end up with -8x minus 11. And since this has an expression, it's an expression with x, it's actually going to be equivalent to this original. I'm going to rewrite it as an equation because I didn't just evaluate it for a number. So I don't want to leave it without the, like the y equals, or in this case, the f of g of x. So there's our answer for that one. So let's look at two more that are like this. So this one here, we have g of f of x. So it's basically the same thing as what we just did. It's just backwards. So we're going to do it in opposite order. And again, we don't expect to get the same answer because we know that these are not commutative. So we're going to start off with taking x and plugging it into f. So we have g. And then we go up here and we look at f of x, which is 2x plus 1. If you plug x into 2x plus 1 for x, it's just going to be 2x plus 1. So it just ends up being the same thing. So 2x plus 1. And now you're going to take 2x plus 1 and you're going to plug it into function g. So function g is -4x minus 6. So this is going in to -4x minus 6. Notice when I said x, I put a set of parentheses because that's what we're going to be plugging into. So now I'm going to take my input and input it into the function g for x. So now you can, at this stage, just go through and distribute and simplify. So we get -8x minus 4 minus 6, -8x minus 10 is the answer for g of f of x. So there we go. And you notice you didn't get the same result because these are not commutative. So that kind of just verifies for you that you don't get the same result. So changing the order does matter. So let's look at this last one. We have f of g of x plus 1. So first thing we're going to do is we're going to take x plus 1 and we're going to input that into function g. So let's go ahead and do that. We'll keep this f of with parentheses. And in function g, so function g, we have negative 4x minus 6. So I'm going to have negative 4x minus 6. And wherever that x is where I input this x plus 1. And now we're going to simplify this stuff in blue here. So I'm going to just kind of carry down this f of, because I got to remember whatever I get out from g of x plus 1 needs to then go into the function f. So we get negative 4x minus 4 minus 6. So we end up with f of negative 4x minus 10. And now we're going to input that into function f. So this is all going into function f. So function f is 2x plus 1. So it's going to be 2x plus 1. So the input goes here. So the input is negative 4x minus 10. And now we just are going to simplify. So we get negative 8x minus 20 plus 1. So we get negative 8x minus 19 as our answer. And again, since this has a variable left in it, let's express it as an equation. So g of x plus 1, f of g of x plus 1 is equal to negative 8x minus 19. So now the last thing we're going to look at is, well, what happens to the domain? So if you remember, when we talked about operations, we also talked about the domains after we did the operations. We didn't do it yet, so let's go to the next page and we'll talk about that, since it's a little bit different for compositions than it is when we're doing addition, subtraction, multiplication, and division with the functions. So first thing we're going to do is we're going to actually go through and do f of g of x. So let's start with that. So we'll figure out f of g of x. So we have g of x is going into function f. So we're just going to start with f of g of x. So g of x is the square root x minus 2. And again, we're taking that and we're inputting it into function f. So function f is x squared. So again, wherever you see the x, those are your parentheses, because that's where your input is going. So the input is this x, square root of x minus 2. And now you just simplify this. So if you square a square root, we know that those cancel each other out, so we're left with x minus 2. So that means f of g of x is equal to x minus 2. So now what it asks us to do is to find the domain. So how do we go about finding the domain? And if you remember when we talked about the operations, we talked about the domains needing to be the same when we're adding two functions, and then the final domain is actually going to end up being the same thing. So for this one, we're going to kind of use that same idea, that you have to take into consideration the domain of the input and the domain of the final result, and take whatever is most restrictive. So for example, if one of the pieces here has a domain of negative infinity to positive infinity, but one of them says you can't include 3, we can't include 3 overall. It was similar to the division problems. The domain of the numerator and the domain of the denominator are often all real numbers, but then when you get down into dividing them, the domain of the entire function is restricted because you can't have 0 in the denominator. So we're going to look at that first as looking at g of x, because g of x was the input. So if you remember, this was the input. So since we inputted this into the function, we have to take the domain of this into consideration. So we need to check for domain restrictions. So since we have a square root, we know that we can't have a negative under a square root. So since g of x, let me just rewrite it, has a square root, we know that this stuff underneath cannot be negative. So that means there's a restriction. So that means I'm going to take this stuff underneath and make it so that it's greater than or equal to 0. So positive or equal to 0. So x must be greater than or equal to 2. So that means that the domain of g of x, notice I'm putting g of x as like a little subscript, the domain of g of x, just so it's easy to keep it straight. The domain of g of x is actually going to be 2, including it, to infinity. So then what I need to do is I need to compare that to the domain of this function here. So if you look at this function, we got out x minus 2. So if you think about x minus 2 is a line with a slope of 1 and a y-intercept of negative 2. And there's no domain restrictions. It's not a square root. It's not a fraction. So the domain of this function is going to be negative infinity to positive infinity. There's no restrictions. But when you go to write the domain for the entire function, the composition, you now need to take into consideration both of these. So even though I ended up with something that has all real numbers as a domain, because I inputted this square root of x minus 2, and because we're looking at this as a composition, we have to take whatever is most restrictive as our domain. So that means the domain of f of g of x is actually going to be 2 to infinity, because we can't include these negative numbers because of the restriction over here. So let's just look at one more example like this. So for this one, we're going to start off with finding f of g of x. So we're going to take g of x, again, as the input into function f. So it's going to be f of 2x plus 3. So we're plugging that into function f. So function f is the square root of x. So you're going to input the 2x plus 3 into the square root. And then you simplify, which in this case I can't really simplify. The only thing I could really do if I wanted to do anything would just be drop the parentheses. So now what we're going to do is we're going to look at the domain. So the domain of our input, we always have to check. So check this for domain restrictions. And this function for g of x is actually a line, 2x plus 3, or mx plus b. So there's no restrictions. So that means that the domain of g of x this time is just going to be negative infinity to positive infinity. So then we compare that to the domain of this. So in this case, now we have restrictions because we have a square root. We know that this stuff has to be greater than or equal to 0. It can't be negative. So now when I go to find the domain of this, it's going to be different than negative infinity to positive infinity. So 2x plus 3 is greater than or equal to 0. So let's go ahead and solve this. Bring the 3 over. Divide everything by 2. That tells me the domain of this part that I got out has to be x is greater than or equal to negative 3/2. So we have negative 3/2 in a square bracket because we want to include it to infinity. So then when we look at the domain of the entire composition, we have to compare these and take what's most restrictive. So the domain of f of g of x, or of the entire thing, is going to actually be what's most restrictive, which is this negative 3/2 to infinity.